Well, welcome everybody. We're going to talk about some new advancements in the topic of transfer path analysis for the latest revision of Testlab in 2506. And really the big news here is that transfer path analysis is making its first incarnation in Testlab Neo. So if you have made the leap to Testlab Neo, transfer path analysis in its first generation is now part of Testlab Neo. That's what I'm going to focus on today. Just give you a little bit of a sneak preview as to what's there right now and then what is coming in service level 1 as well as future versions. So just to start 10,000 feet away, talking about the topic of transfer path analysis, this is, if you're unfamiliar, we have our sources in our system, we have transfer paths, or the ways in which the energy from our source makes it to our receiver. And this receiver is typically a microphone or an accelerometer, some place where usually an operator is going to experience either the noise or the vibration or both of this device. And so our sources are typically engines or motors or airborne noise sources, that kind of thing. Paths, or the transfer paths, are typically either structure-borne paths through the physical structure, so where the source mounts to the device. If they're airborne paths, it's literally the air path between the surface of the source to our microphone location in the driver's compartment or wherever our receiver might be. We break our system down in terms of all these paths of structural paths and airborne paths, and we then hopefully break up the energy between all of these so that we can do one of these sort of contribution analyses. We want to see who's responsible from a path standpoint for transmitting the most of the energy that's either causing our noise or vibration or noise and vibration problem. So that's what we're doing in transfer path analysis. In traditional transfer path analysis, we are computing something called a contact force or an interface force, and we use several methods to estimate these. This is one of the reasons we do the transfer path analysis, is to calculate some operational loads at that connection between our source and our receiver. There are a couple ways we traditionally do this, and these methods that I'm going to explain now are going to be important when I talk about what's in TPA and Neo in 2506 and what's not quite there yet. So we have the direct method where I've got a source and I've got a receiver, and I want to measure the forces directly, so I can just put a load cell in between those two. I'm going to measure my forces directly. This isn't always feasible, as introducing that force transducer might change the system and how it behaves. And so we have other methods that aren't quite so intrusive. They're a little bit less direct, a little bit more indirect in force estimation methods. One of these is mount stiffness. So if we have an elastomeric mount between our source and our receiver, we can measure acceleration both on the source side and the path side or the receiver side of that mount, measure the acceleration, double integrate to get displacement, and then multiply that by the dynamic stiffness of that mount. F equals Kx. We can estimate the forces by measuring on either side of the mount and then multiplying by the stiffness. That requires us to have that dynamic stiffness curve, which isn't always very high fidelity or even possible to get. And we're making some assumptions about how the forces are translated through that mount. So there is another method called matrix inversion, where we're not going to worry about having that mount stiffness data. We're just going to measure some additional transducers here on our receiver structure. We're going to call these indicator measurements. And they're just going to help us quantify what this force is during operation by making some additional measurements. And so we're going to do this matrix inversion, essentially creating a matrix of FRFs between this input force or input location on our path to these indicator locations. In traditional TPA, we'll take the source out and then we'll use an impact hammer or something and actually get FRFs between the connection point and our indicator locations to understand that relationship. We can then invert this matrices. So these are A over Fs from this connection point to 3, 4, and 5. And then we would invert that, so we'd have F over A, or force over acceleration, multiply that by our operational A, and then we should be able to derive a force. Okay, so that's traditional TPA. That's matrix inversion. It's a very popular method. When we talk about blocked forces or invariant loads, we have the same load estimation techniques. We have the direct method. In blocked forces, we're trying to establish what the forces are that are properties solely of the source. So we can pin this source down and mount it to a infinitely massive, infinitely stiff fixture and measure those forces directly. Again, not always practical and almost never possible, in the fact that we can never build a structure that's truly going to be infinitely stiff and infinitely massive. And so there's always going to be some dynamics in our structure there, but people do build very stiff structures that are good up to a certain frequency, and they do make these direct measurements. That's called the direct method. There's also a way we can use free velocity, which is similar, but there we're not using any constraints and we're measuring accelerations. Most popular, because it's the easiest to realize in a realistic way, is we're going to do this thing called in-situ TPA, where we're going to use our source on some receiver, and the theory tells us that it doesn't matter what receiver we use. We can do some mathematic tricks and back out the dynamics of this receiver to get us to this blocked force that is a property solely of the source itself. So there are two main branches of transfer path analysis. There's traditional, where we're calculating these contact forces. Then there is what we call component-based TPA, where we're really calculating these things called blocked forces. In-situ TPA is really using matrix inversion as part of it, and so it's very similar to the matrix inversion method we talk about in traditional TPA. So it doesn't matter whether we're calculating a contact force or a block force, matrix inversion is one of the ways we can get there. Transfer path analysis in Neo, some of the challenges with where transfer path analysis has been in Testlab software so far. It wasn't the easiest or the most flexible to perform multiple analysis variations with a TPA model in Testlab Classic. If we want to compare multiple settings or different analysis techniques, we can do it. It's just a little bit more involved and a little bit less convenient. And so that was a challenge. And then how do we document the quality of our analysis? For doing matrix inversion, there's some quality numbers we can calculate on how well that matrix is conditioned and the inversion process. We don't really keep track of those quality metrics, at least in previous versions. And so there's a new TPA interface in Testlab Neo. And moving it to the new interface of Neo provided us some opportunity to add some of these features or change the way that the software interacts with our data. One of the nice things right off the top that I'll show you is we can define multiple TPA models, and we can define multiple FRF sets, define multiple operational sets, and then we can very flexibly build TPA models using different data sets. And I'll show you that process in the software demo. We then can batch process a bunch of these different combinations, and they're all in one place, and so we can compare them more directly. This just makes it more convenient to compare different approaches, different settings, including different FRFs or different data. And we also save those quality metrics, so we have some record of how well our matrix was conditioned before we inverted it, that kind of thing. Because this is the first release, we did focus exclusively on the direct method. So if you do have the ability to measure or simulate direct loads between your source and your receiver, you can do that in Testlab Neo TPA. And then the matrix inversion method is also included in Testlab Neo TPA. Maybe most straightforward in the direct, and then maybe one of the more popular in matrix inversion. Coming next release will be the mount method and some of the other options we have for that. If you're familiar with TPA in Classic, it's just helpful to maybe see where we've been. If you've done TPA in Classic, this is not unfamiliar to you, and you know the pluses and minuses of this interface. If you are new to TPA, there are a total of at least 5 steps, I would say. So you have this TPA model tab, and in this tab, we're going to define this TPA model. We would then go through the definition. We'd then select our FRFs. We'd select our operational data. Then I would move to the TPA loads tab, calculate those loads, and then I would move to the TPA results tab, and then I can look at the results of that model and those loads that I calculated. So not the most direct or maybe limiting the number of clicks type approach. It's a little bit more interactive, let's say that. So in Neo, we really only have 2 steps, and there's the definition and the analysis tab. On the definition side of that, we're going to build our TPA model. We're going to select our FRFs, and we're going to select our operational data. And again, one of the cool things about Neo is that I can create multiple models using different FRF sets and different operational sets. So it's not just 1-to-1 to 1. I can create different combinations all in one place. And then in the analysis tab, I have all of these different analyses all in one place, and my results are all in one place as well. And so I can look at my traditional results that way. In the definition step, we'll have a flat list of our degree of freedoms. We then assign them to their different roles, be they indicators, targets, or paths. I'll show you that. This process is really pretty straightforward. I'm not going to spend a bunch of time on the slide. I'll show you this in the software, but this makes a good reference for you. One of the other cool things that I think is really helpful is there's also this extra support dialog box that gets populated in the software. And so if you're new to TPA or you don't do it very often, and so you're always having to relearn the whole process when it is time to do it, we provide a little bit more guidance right in the software in terms of the data you need and what you're ultimately trying to do, and to connect all the boxes and get a useful answer. Definition. Let me just see if I can figure out which one I want. Oh, here it is. Okay. This is a blank project, and I just copied some data in. And I'm going to build my TPA model from scratch here just to show you what this process looks like. In this project, I have 2 different sets of FRFs. In this case, my source is a little wiper motor from an automobile, and I've got a little structure that I am using as my receiving structure that I am taking measurements on. Some indicators as well as some target locations on that little aluminum structure that I'm bolting this wiper motor to. So I've got 2 different sets of FRFs, with a bar and without a bar. I'm going to focus on this with bar. I'm really just modifying my structure and measuring these FRFs twice because I want to be able to calculate block forces. That's not always required. That's why you see 2 different sets of FRFs there. But I've got FRF sets, I've got operational data sets. So this is a constant speed, 3000 RPM. And then I've got a bunch of frequency spectrums at those different locations and directions. And I've got operational with bar and without bar. So I've got FRF sets, operational data sets, and then because I want to quantify my block forces and compare that to background noise, I also have measurements without the source running. So that's where I'm going to get my FRFs without the source on. So I have both operational and system data where the source is not running. My first step is I need to turn on or add in transfer path analysis. So if you go to add-ins over here, I only have transfer path analysis turned on. If you're familiar with using this product in Classic, the number of tokens is the same, 98 tokens, and that's where I turn it on. In doing so, I get this other tab here, so I click on that, and then I just have these 2 steps, definition and analysis. And so first step is I need to build this TPA model here, right? So this TPA data set says, this is all the stuff you're giving me to build this TPA and do this analysis. All of that shows up here. Here's my project down here. I'm going to add some of this stuff from my project into this TPA data set. I'm going to use one of my FRF sets to build that model. And the model is really just a definition of here are all the degrees of freedom that are in the data I am going to be supplying. These are going to be the targets, these are going to be the indicators, and these are going to be the path locations. Okay, so that's what I mean by building the TPA model. If I right-click right on this folder of FRFs, I have three options: add to TPA model, add to FRF dataset, or add to operational dataset. These are the three steps I have to go through. In this case, I'm going to add them to TPA model 1. If I now go up here, I see I have TPA model 1. If I click on that, this pivot table view or this contents view updates to show me what I have in that TPA model. And you see this TPA point type column. These are all unlabeled as of yet. And so that's my job here. It's automatically, by default, breaking these up by quantity of measurement. Okay, so you see moment of force, force, and in this case, acceleration. I could also have pressures here. I could also have volume acceleration. If I had airborne paths, in this case, I'm just working on a vibration TPA. And so all of my FRFs are either force, acceleration, or A over F. And over here on the right-hand side is that guidance graphic. You can say, I'm doing an in-situ TPA, I'm doing a matrix inversion, where they kind of go through the main steps. Operational, you have both the source and the receiver. For your FRF measurements, you want to remove your source and take your FRF measurements right on your receiver. Direct, they're explaining again the two steps you have to go through. An in-situ TPA, this is what I'm doing today. I'm going to calculate block forces, so I never remove my source. A little bit of a guidance feature for people who may be newer, or a refresher for people who don't do it very often. So my forces, I just multi-select these using the shift key. I can right click and I can say, these are my paths. All the forces or moments of force are all going to be the input to my path. All of my path FRFs are A over F, either in a translational degree of freedom or a rotational degree of freedom. I have responses, which are acceleration, but my input is going to be the force. And so that's how I know I want to make these my path definition. I named these points T as target and I for indicator. Okay, so these are just the different locations. I know these 4 directions are my targets. So I assign those as targets, and then I assign these guys as indicators. Okay, this is my TPA model. I can choose and create a second model if I want, TPA model 2 or whatever, and maybe I don't include all of these different channels or degrees of freedom. Maybe I restrict it to a smaller data set, or I add additional ones or whatever. That's up to me, and I can do those sort of flexibly right here. I've now defined my TPA model, so now the other things I need to do up here is populate something in my FRFs and populate something in my operational data set. With my operational data set, I'm going to focus on this width bar, at least as far as building the model is concerned. Operational data set, I'm going to add this to an operational data set, and I'm going to call this width operational width bar. Okay. Then I'm going to do background. I'm going to add this to an operational data set and call this background width bar. So I now have 2 different operational situations added to my operational. And then I'm going to add my FRFs into my data set. I'll call this no bar. Oops. And width bar. Okay. These I don't need. These are empty ones. I wanted to name my own, and so I'm just going to delete those and clean that up a little bit. So now I can click over here on my TPA data set, and that consists of a model, FRFs, and operational. I see my model here. I click on my with bar FRFs and I see I've got a bunch of data in there. There's all my FRFs and I'm mixing units there, so it doesn't like that. So there's my rotations. Here's my translations. I see all my data's in there. That gives me a good feeling. Here's my operational data. Looks great. With bar, and here's my background with bar. So I see that all my data's in here. The next step is to go to analysis. Now, if I jump back to this, just sort of show you in the slides what we're about to do, is we're going to create something called an analysis. And this is a little bit different than classic. And so I'm just going to take a second to describe what I'm doing. The analysis task is composed of three parts: the model, the FRFs, and the operational data set. Take these three parts that I just populated with data, and I'm going to create an analysis. Now you noticed I had operational with bar, operational without bar, background with bar, background without bar, and then I had FRFs of both with and without the bar. So I've got a bunch of different combinations. I can create those different analyses all using the same TPA model, but different FRF and operational set combinations. And I'll show you that in the software here. This is the analysis task up here. I'm on the analysis tab. So I'm on the second half of the TPA major task here, and I'm defining. So I click on analysis 1, and it has looked in my TPA analysis location in the software, and it's pre-populated with some assumptions. I'm going to name this something else in just a minute, but here's where I select my method. I can either do matrix inversion or direct. For the matrix inversion, it tells me an overdetermination quotient, and this means just how many more indicator locations and degrees of freedom do I have than targets. I want this to be overdetermined. That's going to give me a sort of metric of those. These targets, paths, and indicators, these are pre-populated based on these assumptions that it made down here. I can select my FRF data set here. I can either choose with bar or without bar. I'll do with bar first. My operational data set is, I'll do operational with bar. See the frequency range, some saving options, etc. So I'm going to call this analysis operational with bar. And I have a new analysis up here. Now I can create a new analysis, or I could clone this one, and I'm going to call this background with bar. Okay, so what do I want to change? I don't want to change my FRFs because I'm doing the with bar scenario. I just want to change my operational to the background with bar. Okay, so now I have a second analysis, and I could continue doing this. I could say clone that one again, and I want to change this guy to operational without, I'll call it no bar. So here I want to change my FRFs to no bar, and this is operational. Oh, I never added those. So I can't do all four combinations, but you get the idea. I would change this to operational without the bar, and I can create 4 unique analyses in here and then batch process those all at the same time. Once I do that, and I'll show you this in just a moment, once I do that, you see these analyses are either in different states. I'm still defining these analysis 2 and analysis 3. This one says processed, and so I have some results. I have this analysis view where I was clicking on either new or clone. This extended view, I'll show you that in just a minute. That just shows me more data up here that's copied from down here. And then in my definition, I've already done these steps, but I could also recheck those definitions by using these shortcuts in the ribbon. And now that I've done a process run, I can look in this results area of the ribbon, look at my loads I calculated, look at their different contributions, as well as check the quality of my calculations. So this just shows you where all these pieces of data come from. Again, this will act as a nice reference for you if you need to check back. And then this just shows a summary of where the different sources of data come from and what they look like. Now I want to move over here, and I've got some analyzed results. And so here are my process results. So you see I have both operational with bar, with no bar, background, no bar, and with bar. And I can look at some different types of plots here. So here in the loads, contributions, and quality, you see it automatically loads that type of data by clicking on that view, loads or contributions, etc. So in this case, I have 6 blocked forces that I calculated in translations and rotations. These are the loads that I calculated by providing it operational data with background noise and then in operation. And I really have 4 sets of analyses here. So whatever I have highlighted over here is what's going to be populated here in this pivot table for my loads. So if I just want to see operational loads with and without the bar, I have that in this view right here. These are the 6 degrees of freedom. Front are my rotationals, in the back is my translational forces. These are the blocked forces with no bar. If I click over here, these are the same 6 degrees of freedom blocked forces with the bar. If I compare these 1 to 1, I see the blocked forces are very similar between with bar and without the bar. And so my receiving structure has changed. The theory of blocked forces tells me that my blocked forces should be the same regardless of what receiving structure I have them on. And I can compare those directly, and I see very nice agreement in terms of the content and the level of my blocked forces between the different degrees of freedom. So these are properties of just that wiper motor. The structure has been backed out, and these are my blocked forces. Under contribution, I can certainly look at the FRFs this way. Isn't quite as helpful. I can generate a new plot, and if I do a function map, and if I want to compare, let's say, name and add a run name to a quantity here, you can always add new columns to your pivot table. If you didn't know that, just hit this plus sign. And so I see RPM with bar and no bar. I'm just going to look at the with the bar case in this case, and I see my 4 different targets up here, and I can just take all 8 and I can see the contribution display of the different paths for my measured target location. I can rank and investigate my sources that way, or the paths rather, like I do in Testlab Classic. So that allows me to rank order my paths, see who's contributing, which directions are most responsible, and that might give me some clues as to how I address either on the source side or on the path side to solve my problem. So those are the different things I can look at up here. Again, this will break down for you all the different pieces between partial contributions, total contributions, those quality metrics we calculate as part of the TPA calculations, and all of the different pieces that we've used and all these intermediate answers that we get when we do this transfer path analysis. Well, that's what I've got. That's a sneak preview for Testlab Neo and transfer path analysis in Neo. If you are a TPA user and you have access to 2506, I encourage you to go play around with it. If you have any questions, feel free to reach out. My email's on the screen, and I'd be happy to help you out if I can.